In this video, I just want to give a quick bird's eye view of the oxidation and reduction reactions in this chapter. In future videos or in previous videos, in the case of reduction, I'll go into more detail about the mechanisms of these things. But in this video, I want to talk about these reactions just from the perspective of synthesis. So that's pretending you're a chef, you're going into a sort of laboratory kitchen. What do you need to take off of the shelves of your kitchen in order to accomplish certain transformations? Now, these transformations for oxidation and reduction are going to happen through three functional groups that we've seen already. The first one is the star of this chapter, alcohols. The second one is aldehydes, and the last one is carboxylic acids. Now, what we've covered so far are reducing agents. If you look at the carbon here, in carboxylic acids, it's bonded to 3 electronegative elements. In aldehydes, in carboxylic acids, it has 3 bonds to electronegative elements. In aldehydes, it has 2 bonds to electronegative elements, and in alcohols, it has 1. So as you go from the right to the left here, as you go from the right to the left, the number of bonds to electronegative elements decreases, and so this is reduction. Now, we've seen 2 reducing agents. We've seen a weak reducing agent, and we've seen a strong reducing agent. The weak reducing agent was sodium borohydride, and the strong reducing agent was lithium aluminum hydride. What this means, weak and strong in practical terms, is that sodium borohydride can reduce aldehydes or ketones to alcohols. So note that aldehydes or ketones have 2 bonds to an electronegative element, alcohols only have 1, and so that's a reduction. The strong reducing agent, lithium aluminum hydride, that can reduce almost anything to an alcohol. So it could reduce aldehydes, or ketones, or carboxylic acids, or esters to an alcohol. And we've seen that in previous videos and in previous exercises. Okay, so much for reduction. That's if you reduce the number of bonds to an electronegative element. That happens as you go from a carboxylic acid to an aldehyde to an alcohol. What if you go the other way? What if if you go from an alcohol to an aldehyde to a carboxylic acid? If the number of bonds to an electronegative increases, so that here there's only 1, here there's 2, here there's 3. In that case, you have the opposite of reduction. You have oxidation. Now, we haven't talked about these reagents at all, either what they are or how they work. In this video, I just want to mention what they are. We're going to see how they work in the mechanism in a future video. Just like with reducing agents, you have a weak oxidizing agent and you have a strong oxidizing agent. The weak oxidizing agent is going to be something called PCC. Now again, we'll see the structure for that. We'll see what it stands for, what it means, how it works in a future video. It's called pyridinium chlorochromate. You almost always call it PCC. Sometimes they'll mention the solvent that it's used in. The solvent is methylene chloride. It's very important that you never use that with water. And when you see the mechanism, you'll see why. It would not function in the way that you want it to as a weak oxidizing agent if you put it in water. So you could either write just PCC or PCC in methylene chloride. Methylene chloride, by the way, is just 1 carbon with 2 hydrogens and 2 chlorines on it, and it's really toxic. It looks like water, so it's just a clear liquid, but if you ever deal with it, make sure you don't take it out of the fume hood. It's neurotoxic, it's carcinogenic, like a lot of the stuff we're dealing with. That's also true of PCC and of the strong oxidizing agents that we'll introduce right now. Now, there's only one strong oxidizing agent that we're going to cover here, but there are multiple ways of writing it. So notice there's chromium in each of these. These are all going to be the same thing, even though they're being written in a different way. And I'll show you how these can interconvert in a future video. But one is chromium trioxide in the presence of water. That's one way of writing the strong oxidizing agent. Another way of writing a strong oxidizing agent is chromic acid, H2CrO4. If you're familiar with sulfuric acid, H2SO4, notice this is the same kind of idea, but instead of the sulfur, you have the chromium. And then the other way to write this is either as sodium dichromate, Na2Cr2O7, or potassium dichromate, so K2Cr2O7. Okay, so these are our reagents. Now, just like before, we had strong and weak reducing agents. These are strong and weak oxidizing agents. Now, what do those words mean in this context? In practice, what difference do these make? PCC, the weak oxidizing agent, will take a primary alcohol and it will turn it into an aldehyde. So notice, a primary alcohol could be oxidized to an aldehyde. That's just being oxidized once. So you have one bond to an electronegative element. Here you have two. So it's really just being oxidized once. Compare that with what the strong oxidizing agents do to a primary alcohol. That strong oxidizing agent would take a primary alcohol all the way to a carboxylic acid. So you'd go all the way, as oxidized as you possibly can be. You'd go from one bond to an electronegative element to three. And the truth is, as you'll see in the mechanism, first you form the aldehyde and then that gets oxidized again to form the carboxylic acid. So that's how these are different in terms of working with a primary alcohol. Now when I say primary alcohol, what I mean is an alcohol, so an OH, whose carbon, the carbon that the OH is on, is only bonded to one other carbon. So that's a primary alcohol. Compare that with a secondary alcohol. So here, you can see this alcohol here, the carbon that has the OH on it is bonded to two other carbons. That's secondary. Now, the strong and weak oxidizing agents are only different for primary alcohols. If you have a secondary alcohol, they both do the same thing. They both turn that alcohol into a ketone. So that's true for PCC. That's true for these chromium oxidizing agents. Another thing I'll mention is in this test, in this chapter, you could see this written in any of these ways, but in future tests and chapters, I'm going to be using sodium dichromate. So that the strong oxidizing agent will turn a secondary alcohol into a ketone. So you can see that ketones cannot be oxidized any further. Primary alcohols could be oxidized to aldehydes, those could be oxidized to carboxylic acids, but secondary alcohols can only be oxidized to ketones, and it can't be oxidized any further. And again, we'll see the reason for that when we go over the mechanism for how these work in a future video. For these strong chromium oxidizing agents, you might have run into these before. Sodium dichrome, like a lot of organic compounds, they can be very toxic. So if you're working with these in the laboratory, be extremely safe. Make sure you wear gloves. Make sure you don't take this stuff out of the fume hood. Sodium dichromate is actually the star of the movie Erin Brockovich. You thought that it was Julia Roberts. Actually, it was sodium dichromate. Sodium dichromate is a chemical that the chemical plant that was being investigated in that movie was using to oxidize stuff. It was doing oxidations, and it got leaked into the water supply of the town that it was in because they weren't disposing of it responsibly. And then people ingested it, and it gave them cancer and birth defects and things like that. So that's where you might have run into that before. And if you've ever seen the brilliant yellow in the sunflowers or cornfields of a Van Gogh painting, that brilliant yellow is coming from potassium dichromate, which was a molecule that was included in the paints that Van Gogh used. So you might have run into these before. Okay, So this is our bird's eye view of oxidation and reduction reactions. Reduction is where you go from a carboxylic acid toward a primary alcohol, or a ketone to a secondary alcohol. And you could either use sodium borohydride or lithium aluminum hydride. Oxidation is where you form more bonds to an electronegative element, like oxygen. So you'd go from a primary alcohol to a carboxylic acid, or a secondary alcohol to a ketone, and you would either use PCC or one of these chromium reagents, like chromium trioxide, chromic acid, or sodium dichromate, or potassium dichromate. Okay, this is the broad overview. We're going to zoom into some important details about each of these. We'll see how the oxidizing reagents work in future videos, and then we'll bring it all together, apply it to some synthesis problems in the exercise for this chapter.